All right, so the warm-up today, simplifying radicals. Again, we're getting back into some quadratics, and we're bringing in that imaginary part. The parts of quadratics that we have to look at is the parts that deal with radicals, because the imaginary part comes in when we have a negative number under the radical. So that's why we're going back and reviewing. These are all positive numbers under the radical, so this is just a simplifying that we were doing before. We're looking to see, are there any perfect squares within these numbers? How can we simplify them? When we get into the notes today, we'll take a look at how do we deal with that negative one. We talked about it yesterday in our notes, but we'll look at how that actually looks in practice. So when I'm looking to simplify the square root of 24, I'm trying to find out if there's any perfect squares of 24. Well, my perfect squares that are lower than 24 are 4, 9, and 16. So I'm looking to see if any of those go in, and if more than one goes in, the largest one that goes in. So if 4, 9, and 16, do any of those go into 24? 4 does. So 4 times 6 . 4 is my perfect square. 6 is 2 times 3. I know that 2 and 3 are not perfect squares. There's nothing that I can simplify there. So the square root of 24 is the same thing as saying the square root of 4 times the square root of 6. I know that the square root of 4 is 2 times the square root of 6, which just leaves me 2 radical 6 as my simplified. Again, I'm looking for perfect squares within the factors of that number. The second one, the square root of 128. So 128, I'm looking at 4, 9, 16, 25, 36, 49, 64 would be the last one. Do any of those go into 128? 64 is the largest. It does have, I think, 4 also goes into it. I don't know if 16 does as well. Yeah, actually 4, 16, and 64 all go in there. But again, when we're looking at simplifying radicals, we're looking for that largest perfect square. So 128 would be 64 times 2. So that is our perfect square. So the square root of 128 is the square root of 64 times the square root of 2. And if you wrote it the 2 first, which is fine, it's just at the end, the radical is always going to be the second number. Square root of 64 is 8 times radical 2. So this would just be 8 radical 2. And then the third one, the square root of 72. Again, if I'm looking 4, 9, 16, 25, 36 would be the largest one that I could look at, because any of the other ones, even if I doubled them, would be larger than 72. So what is the largest number there that goes into 72? Yeah. This is 36 times 2. And 36 is that perfect square we were looking for. So the square root of 36 times the square root of 2 equals 6 times the square root of 2, or 6 radical 2. So again, the idea when we're simplifying radicals, we are looking for the largest perfect square that is a factor of that number to simplify it. Again, we will also be adding in the idea of it being a negative number under the radical and how we will handle that with the imaginary part. All right, we are going to move to page 9 to the notes solve by taking the square roots. All right, so the skill solve by taking the square roots is a skill that we looked at in first semester when we were dealing with quadratics. Again, now we're going to be adding another element to it, but we're going to start reviewing what does this mean. So ax squared plus c equals 0. And this is when there's no x term, where we don't have that bx in there. In a quadratic equation, we can solve using the square root method. So we're going to isolate the squared term, and then we're going to take the square root of both sides. Same thing we talked about when we did for this in first semester. And not every answer today is going to be an imaginary answer. There's going to be a mixture of some that are rational, irrational, and imaginary. So I don't want you to think that the I is going to pop up in every answer here. So some examples of what I'm talking about. If we have something like x squared minus 2 equals 14. There's an x squared term, but there's no x term. So my goal is to get that x squared term by itself. So I'm going to add 2 to both sides. So x squared equals 16. Now that I have the squared term on one side, the constant on the other, I can take the square root of both sides. So x is going to equal, and remember we're taking the positive and negative square root of 16. This one happens to be a perfect square, so this would just give us x equals plus or minus 4. So that is telling us that our parabola crosses the x-axis at -4 and at +4. Those are our two zeros, solutions, roots, x-intercepts, whatever you want to refer to them as. It is telling us where it crosses the x-axis. Now, if it's imaginary, we know it's not crossing the x-axis. It's giving us two other points that you'll learn more about next year. And here's another example, x squared minus 3 equals 12. We're going to add 3 to both sides here, so we get that x squared term by itself. So we get x squared equals 15. Now that we have the x squared term isolated, we can take the square root of both sides. So x equals plus or minus the square root of 15. And when I look to see if I can simplify the square root of 15, the only way to make 15 is 3 times 5. Those are both prime numbers. There's no perfect squares. So I would just leave it as plus or minus the square root of 15. But again, this method only works if we do not have an x term. In the next lessons, we'll learn what do we do when we do have the x term. And you're going to see some of these have just a little bit of work to them, and our last two problems are quite lengthy in doing all the math that we need to do. So it says solve each by taking the square roots. So this first one, I need to add 6 to both sides to get that squared term by itself. So I have x squared equals 42. Now that I have the squared term by itself, I can take the square root of both sides. So x equals plus or minus the square root of 42. When I look to see if there's any perfect squares in 42, it's 6 times 7. I know 6 doesn't have any perfect squares. 7 is prime. So I can't simplify the square root of 42, so that actually ends up being my answer. X equals plus or minus the square root of 42. Number 2, x squared minus 4 equals 8. We're going to add 4 to both sides. So x squared equals 12. Now that I have the x squared term isolated, take the square root of both sides. X equals plus or minus the square root of 12. Well, I know that 12 does have a perfect square because 12 is 4 times 3. So 4 is that perfect square. So x equals plus or minus the square root of 4 times the square root of 3. So x equals plus or minus 2 radical 3. So again, we haven't even gotten to the imaginary part. This is just reviewing the skill of solving by taking the square root. Number 3, x squared minus 4 equals 83. Start by adding 4 to both sides. So x squared equals 87. Take the square root of both sides. So x equals plus or minus the square root of 87. If I try to factor 87, the only way to make it through multiplication is 3 times 29, which are both prime numbers. There's no perfect squares. So x equals plus or minus the square root of 87. Again, not all of them are going to be that simple. Number 4, 64x squared equals 36. I need to divide both sides by 64. So I have x squared equals 36 divided by 64. Take the square root of both sides. So x equals, when you take the square root of a fraction, you take the square root of the numerator and the denominator separately. So this is plus or minus the square root of 36 divided by the square root of 64. So x equals plus or minus 6 over 8, which they can be reduced. I can divide them both by 2. So we get x equals plus or minus 3/4. So just because it's a fraction doesn't mean that we can't do anything with it, that it can't be simplified. You just take the square root of the numerator and the denominator separately. All right, the next page. Number 5, x squared plus 6 equals negative 20. So we need to start by subtracting 6 from both sides. So we get x squared equals negative 26. We take the square root of both sides. So x equals plus or minus the square root of negative 26. But we talked about this yesterday. Anytime I have a negative under the radical, I can take out the negative 1, because we learned yesterday that I equals the square root of negative 1. So I can replace that square root of negative 1 with that I to let the user know it's an imaginary solution, which lets the user know it does not cross the x-axis. So x equals plus or minus the square root of negative 1 times the square root of 26. And again, all I take out is that negative 1. It doesn't affect the other number. I'm going to replace that negative 1 with I. So x equals plus or minus I times the square root of 26, which just leaves us with I equals plus or minus I radical 26. Yes. Yes, the I has to come before the radical. The I will go after any whole number that's not under the radical, which we'll see in a minute, but the I does come before the radical when we're writing it. And just 26, if we were to try and simplify that, it's 2 times 13. There's no perfect squares in there. So that would be our final answer, plus or minus I radical 26. And again, that's telling us we know that that function does not cross the x-axis. As soon as we see that I in an answer, we know it has an imaginary solution, and it means it doesn't cross the x-axis. X squared minus 7 equals negative 17. Add 7 to both sides. So x squared equals negative 10. Take the square root of both sides. So x equals positive or negative square root of negative 10. Again, I can rewrite the square root of negative 10 as the square root of negative 1 times the square root of 10. Replace that square root of negative 1 with I, so x equals plus or minus I times radical 10. If I do a factor tree of 10, the only factors are 2 times 5. Neither is a perfect square. So we just have x equals plus or minus I radical 10 as our answer. Now, we're going to see in this next problem, you don't always have to have a radical left in your answer to have an imaginary answer. It is possible that you can have an answer that does not have a radical in it, but is still an imaginary solution. All right, number 7, x squared minus 7 equals negative 16. We have to add that 7 to both sides to get that x squared term by itself. So x squared equals negative 9. Take the square root of both sides. So x equals plus or minus the square root of negative 9. Again, we can separate out that square root of negative 1. So x equals plus or minus the square root of negative 1 times the square root of 9. So x equals plus or minus, we're going to replace the square root of negative 1 with I. Square root of 9 is 3. Now, when we write this, because there's no radical, the 3 does go in front of the I. So this becomes x equals plus or minus 3I. Again, by having that I in the solution, it is telling me that that function does not cross the x-axis. And you will learn more about these imaginary numbers next year. Number 8, negative 9x squared equals 720. So here I need to divide both sides by negative 9. So I get x squared equals, what is 720 divided by negative 9? Negative 80. So x squared equals negative 80. Take the square root of both sides. So x is the positive or negative square root of negative 80. So x is positive or negative square root of negative 1 times the square root of 80. And if I go to break down 80, I'm looking for any perfect squares. So I have 4, 9, 16, 25, and 36 to choose from. Do any of those go into 80? The 16 is the largest, so 16 times 5. So 16 is a perfect square. So this becomes x equals plus or minus I, because I'm going to replace that square root of negative 1 with I, times the square root of 16 times the square root of 5. So x equals plus or minus I times 4 times the square root of 5. And again, that 4 is going to move in front of the I. So x equals plus or minus 4I radical 5. So yes, order does matter where we're putting that imaginary number. Now the next two are a little bit longer. Okay, there's more steps to them. So 5x squared plus 7 equals negative 47. So we're going to start by subtracting the 7 from both sides. So 5x squared equals negative 54. Then we need to divide both sides by 5. So x squared equals negative 54 divided by 5. If it doesn't divide evenly, just leave it as the fraction. Come in, take the square root of both sides. So x equals positive or negative the square root of negative 54 divided by the square root of 5. Now, if I do a factor tree on 54, because really that's going to separate out to plus or minus the square root of negative 1 times the square root of 54 divided by the square root of 5. 54 does have a perfect square. It is 9 times 6. 9 is a perfect square. So this becomes x equals plus or minus I times radical 9 times radical 6 divided by radical 5. X equals plus or minus 3i radical 6 over radical 5. The problem is I cannot leave a radical in the denominator. We talked about this before. I have to get rid of that radical 5, and I do it by multiplying both the numerator and denominator by radical 5. So I have x equals 3i. Now I have radical 30 because 6 times 5 is 30 divided by radical 25. 30, if I look at its factor tree, is 5 times 6. There's no perfect squares there, so 30 isn't going to simplify. 25 is a perfect square. Oops, I forgot my plus or minus there. So x equals plus or minus 3i radical 30 divided by 5. I know that's a little bit of work there, but you have to remember you cannot leave a radical in the denominator. You have to go in and fix that by multiplying it times itself in both the numerator and denominator. So a couple of these could be a little bit more involved in the work required. Number 10, 5x squared minus 10 equals negative 87. I'm going to start by adding 10 to both sides. So 5x squared equals negative 77. Divide both sides by 5. X squared equals negative 77 divided by 5. Again, once I get that x squared term by itself, I can take the square root of both sides. So x equals plus or minus the square root of negative 77 divided by the square root of 5. So x equals plus or minus the square root of negative 1 times the square root of 77 divided by the square root of 5. I'm going to replace the square root of negative 1 with I. If I look at 77, that's just 7 times 11. There's no perfect squares there. So x equals plus or minus I radical 77 divided by radical 5. But we have that same problem. We still have a radical in the denominator. So I need to multiply both of them by 5. So x equals plus or minus I radical. If we take 77 times 5, we get radical 385 divided by radical 25. Well, 385 was 77 times 5. There's no perfect squares. 77 is 7 times 11, so that'd be 7 times 11 times 5. They're all prime, so there's no perfect squares. So we just need to simplify the denominator and get x equals plus or minus I radical 385 divided by 5. That would be our simplified answer. So again, a few of them could take a little bit more work. We have to remember all of the rules with dealing with radicals. But the biggest thing is if we have a negative under the radical sign, separating out that square root of negative 1 and replacing that with I to show that we have an imaginary solution, which tells us that quadratic does not cross the x-axis.